Okay, welcome back to the ninth episode of our lecture series. Today we'll be talking about why quantum computing exists, what is quantum computing, do we as normal developers need to fear the incoming of quantum computing, and what are its applications. So, quantum computing, as you know, is a very interesting topic. It is a frontier of development these days. So, yeah, let's have a wonderful chat about that subject. But first, let's start by asking a question. Okay, I'll be asking you a question. A bank needs to find one fraudulent transaction, hidden inside 1 billion daily transactions based on a rare pattern. So, in simple terms, a bank, let's assume the State Bank of India, has recorded 1 billion transactions in one particular day, and it needs to find one fraudulent or one error prone transaction. How will it find? I mean, since it's 1 billion, or I mean, it can be any number 1 billion, 1 trillion, 1 gazillion, I mean, any huge number. So, how do you process such a huge number of information without exactly knowing what to search? For example, if I'm giving you the exact time and the exact accounts you have to search, then it becomes an easy task. But without giving you a lot of accurate information, how do you do that? I mean, you need to go through all those transactions to find which one is the error prone or which one is the fraudulent one, right? So that is where quantum computing comes into play. We'll discuss how quantum computing can solve that problem in the slides which are coming up. Okay, so let's answer why quantum computing exists. Classical computing is hitting a physical and economic ceilings, that is Moore's law. Moore's law states that the number of transistors on a chip roughly doubles every 2 years, leading to exponential growth in computing power at a lower cost. Okay, some problems scale exponentially and break classical systems. Quantum computing attacks problem classes, not general workloads. This is not faster computing, it's like a different computing. For example, let's assume I have two computers. One is a normal computer, any Linux or Windows or Mac machine, and the other one is a quantum computer. When, for example, I want to open a file, I want to read the file, I want to do something. In such case scenarios, I don't think you will notice a huge difference between a quantum computer and a normal computer. But then why do we need a quantum computer? I mean, if it's giving the same performance as a normal PC, why do we have to go through the hassle of making one? But before that, let's talk about what is quantum computing. Okay, quantum computing is, as the name suggests, based on quantum mechanics and not binary electronics based on transistors like ones and zeros and stuff. It uses qubits instead of bits. For example, I'm writing some code in JavaScript. You and me, we both know that the machine at its core cannot understand Java. What is JavaScript? So it has to be compiled into a machine language. Then only it can understand. I mean, it can be through. I mean, I'm not getting into the nitty-gritty of how JavaScript works, but at the end, it needs to be translated into a form in which the machine can understand properly. That's it. That means in the language of zeros and ones. That's the language which machines understand in order to execute something. So those zeros and ones are called bits. But what happens here is that quantum computers don't use normal binary bits. They use something known as a qubit. Okay, we'll talk what a qubit is. Qubits can represent multiple states simultaneously. It enables exploration of massive solution spaces in parallel. Okay, now let me give you an answer to our first question. Okay, here a bank needs to find a fraudulent transaction in a group of in like a bank had 1 trillion transactions in one single day. It needs to find out one problematic transaction without knowing the exact details of those transactions, like without knowing who's the sender or who's the receiver or what is the time or what is the transaction number. It doesn't know any of those things, but it needs to find out any problematic transaction, something which looks fishy. So ideally, without having specific information, and you have to run on like a minimum amount of information, what you will do, what any normal computer will do, it will go through all those transactions one at a time. I mean, in the question we have 1 billion, right? So we'll consider 1 billion. So our classical computer will go through each of those 1 billion transactions one at a time. That is the flaw of classical computing. That is the problem. Mainly because it can only check one file at a time. That is, as I said, classical computers use bits. So in bits we have zeros and ones. So it can either be the value of that bit can either be 0 or it can be 1. It cannot be both at the same time. So it can only check one particular operation at a time. But what happens when you involve a quantum computer is, a quantum computer has a qubit, right? And that qubit can occupy any value in between 0 and 1. It can be 0, it can be 1, it can be both. So it can be a plethora of different values. So why is this advantageous? Because we have 1 billion transactions to go through, right? A quantum computer can go through all 1 billion transactions at the same time and find the problematic one instantly. That's why, if you read newspapers or social media articles, you might have come across people saying that quantum computer solves problem much faster than a supercomputer. A problem which takes a supercomputer almost 1000 years or 100 years or 10 years to solve was done instantly by a quantum computer. Why? Because of qubits, because of its basic property. It can exist in any value between 0 and 1. It can be either 0, it can be 1, it can be anything in between, it can be both at the same time. So it can go through all the given inputs, all the given pathways in one single moment. So these are examples of quantum computers I have searched from the internet. I mean, both of them are basically images of the same thing. I think this is an image of the quantum computer developed by Google. Okay. How quantum differs from classical computing? We are just going through what I already said. Classical bits can have 0 or 1, but meanwhile a qubit can either be 1 or it can be 0. It can be any value in between. So it's like probabilistic state until measured. I mean, this is the scientific statement of how you have to say it. I'm just including it here. But the basic terminology and the basic understanding is exactly what I said. Classical scales linearly, quantum scales exponentially. That, as I said, in a classical computer, it has to go through, if there are 10 possibilities, it has to go through each one of them one at a time. It can only process one at a time. On the other hand, if you have 10 possibilities, all 10 will be considered at the same time by a quantum computer. Okay? This is a pictorial representation of how how the qubit works. If you want, you can pause the image, pause the video and just examine it. Core quantum computing concepts engineers must know. Okay, these are the main four. These are the founding pillars of quantum computing. They are superposition, entanglement, interference, and measurement. Okay, superposition. A qubit can either be 1 or 0 at the same time. This lets quantum computers explore many possibilities at once. Like if you have studied physics, you will understand what the superposition is. If you have two waves, okay, with a similar amplitude and a similar frequency, something known as interference happens and superposition happens. Okay, so it's a similar concept like this. The second one is entanglement. Okay, entanglement is a very tricky and it's a very interesting, and it has a big interesting story behind it. I'll tell you in the near future. Two qubits become tightly linked even when far apart. Changing one immediately affects the other. The next one is interference. Correct answers are strengthened during computation. Meanwhile, wrong answers cancel them out. Then measurement. Before checking, the result is only a probability. When measured, it becomes one final definite answer. Okay. This is a representation of entanglement. I mean, even though those particles might be light years apart, if you are doing some reaction, if you're doing some chemical stuff with one particle, it has effects on the other. Okay. scientists, even to this point, cannot exactly predict what the effect is going to be on the other particle, but yeah, they can predict that there will be an effect. So this is the story I was telling you about quantum entanglement and the Einstein-Bohr showdown. Okay, entanglement. This is a definition again. That is, two qubits become correlated so strongly that measuring one instantly defines the other, regardless of the distance. This disturbed classical intuition about locality and cause and effect. Einstein called this spooky action at a distance and rejected it as incomplete physics. The main problem was that Einstein believed that everything in this universe had to adhere a law. I mean, at this point, if Einstein believed that even if he might not understand it, the future generations like us can find solid ways to prove that exists. So even if Einstein could not find that law, he believed that the future generations could. But like baseline, he believed that everything in the universe, every single action, whether it be on the quantum scale or on the macro relativistic scale, had to follow a certain set of rules. But this is what the problem. Okay, let's assume I have a pen. Okay, this is my pen. This is one particle. This is another particle. Okay, so like one particle sitting on this side and the other particle on this side. So if I am giving it a gentle wave, sorry, it fell down. I mean, obviously it's going to affect the other side. But this is one particle. This is one particle. Okay, both my hands are not connected. If I shake this particle, there is no visible effect on this side. That violates Einstein's theorem, because Einstein says if I am moving this finger, I mean, there's a particle, okay, this is a particle, this is a particle. If I'm moving this particle, what quantum entanglement says is that this particle will also feel the effect at the exact moment, zero time lag. But according to Einstein, Einstein's special relativity, nothing, not even any action, not even light, I mean, not even light, only light can travel at 3 lakh kilometers per second. I mean, I forgot the exact number, it's 2.98 to 10 raised to 6, but yeah, nothing's faster than light, not even any movement, not even gravitational waves, not even anything Einstein predicted. So when people came up with quantum entanglement, it fundamentally broke down Einstein's idea of the universe, mainly because, as I said, if both these particles, if I move this has an effect, and if it's with zero time lag, it occurs faster than c, that is faster than speed of light, which of course breaks Einstein's law. That's why he had a major problem with entanglement. So he tried many ways to solve it. He in most famous cases, he had a feud with Niels Bohr, who is known as the father of quantum mechanics. Einstein, along with Podolsky and Rosen, made the theory known as an EPR paradox. Okay, so the EPR paradox argued that quantum theory must be missing hidden variables. As I said, if both these particles have the effect at the exact same time, Einstein believed there is an additional variable which is not discovered by humans at that time. But now it's proven that there is no particular variable. Okay, Niels Bohr countered, saying that reality isn't undefined; it's just not classical. Outcome: quantum mechanics wins experimentally, intuition loses philosophy. Entanglement is now a core computational resource, not a philosophical bug. So this is some scientific nitty-gritty. I'll just go through it very quickly. Inside a qubit, that is hardware reality check. Quantum hardware types. Qubits are built using superconducting circuits trapped inside atoms or light particles. Different approaches, same goals. That is, we need stable qubits. Extreme cooling requirements. Most quantum systems must be kept extremely cold. This prevents random energy from disturbing qubits. Small vibrations like heat or radiation can affect qubits. Even tiny disturbances can break calculations. Qubits make mistakes more often than classical bits. Reducing these errors is a huge challenge today. In quantum computing, algorithms do not calculate exact values the way classical programs do. Instead, they work by carefully shaping probability amplitude so that the correct answers are amplified while incorrect ones are suppressed. These algorithms are represented as quantum circuits made up of quantum gates. Each gate slightly changing the state of qubits in a controlled way. Once the computation is complete, the system is measured, causing the quantum state to collapse into a single classical output that we can actually read. because this result is based on probability rather than certainty. The same algorithm must be executed many times and the outcomes analyzed together to determine the most reliable answer. What is a quantum computer good at? Okay, now we're back to the basic stuff. Quantum computers are generally good at optimization, cryptography, chemistry, and it's bad at creating web apps, databases, current operations, etc. Quantum computers are not a CPU replacement. For example, I have heard many of my friends saying that, like 10 years down the line, you might have a laptop which has a quantum chip inside working as a replacement for the chips made by AMD or Intel or whatever it is. That's not true. It won't work. It can, however, act as a co-processor, not a general computer. So we can talk about how quantum computer is very effective here. Maybe for the first one is cryptography, right? Cryptography means you are securing your password using complex symbols and additional stuff. These days, cryptography is technically safe, but if you are introducing quantum computing into the foray, it becomes very difficult because, as I said, quantum computers can go through billions of outcomes at the same time. So, the current number of password combinations is obviously less than the number of password combinations which properly developed stable quantum computer can go through in 1 second. So no matter how strong your password is, it's gonna break. Considering, I mean, we have a lot of symbols. For example, this is a keyboard, right? So we have a fixed number of symbols here, and each and every permutation combination of those symbols can be easily cracked by a solid, proper, for example, a 64 qubit quantum computer with ease. And the other one is chemistry. So, for example, it can be very helpful in medicine research, especially, I mean, in medicine research, we need to simulate multiple compounds, multiple possible solutions to a chemical reaction, multiple possibilities. So, in such cases, quantum computers are obviously very effective compared to normal computers. Okay, real world applications, like as I said, drug discovery, financial risk modeling, supply chain and logistic optimization, and basically material science and battery research. I mean, chemistry is a stronghold of quantum computing. Impact on software development. Traditional software stacks remain intact. For example, I'm a MERN stack developer, and this obviously says that us MERN stack developers, you can or Python Django or Rust or whatever it is, you will not lose your job. Quantum workloads are offloaded, not embedded. On the other hand, it will create a new section of jobs, people who know how to interact with quantum computing. I mean, I don't know if there is a quantum code available. I mean, currently we're using JavaScript or Java or C program, whatever it is. It's for classical computers, right? So I don't know if something for a quantum computer will come forth, but yeah, if something like that comes, if people can learn it, then yeah, it will obviously open a lot more job opportunities. Quantum programming today. Developers write quantum circuits, not proper applications. Languages resemble Python, but the logic is kind of non-intuitive. That's why I said it's a bit difficult to learn. If people can do it, I mean, if someone finally learns it, then yeah, it's well and good. Debugging is probabilistic, not deterministic. Mental model shift is very mandatory. Skills engineers should start building. Okay, if you want to become a developer in a quantum computing company. These are my vague ideas. Okay, it can be you have to know a basics of linear algebra or how probability works. You know, algorithmic thinking. I mean, you don't have to mug up a lot of syntaxes. You need to be very comfortable with probabilistic outcomes. For example, when I'm writing a set of code for my C program or a JavaScript project or whatever it is, I have a exact outcome in mind. But when you're working with such things, you need to have a vague idea of what your outcome is. I mean, you cannot predict it exactly. It might vary depending on your inputs or depending on, as I said, heat, vibrations. There are a lot of aspects which can affect your output. How modern engineers can adapt. You have to learn quantum basics without abandoning classical stacks. You need to know how entanglement works, how an atom works, the orbitals, etc. How quantum theory works. You need to know how basic understanding of how relativity works, etc. Treat quantum as a service, not infrastructure. Focus on problem decomposition. Engineers who bridge classical and quantum ideologies will dominate. So this is basically a career reality check, that is quantum computers won't, and quantum theory won't replace software engineers. It will replace narrow thinkers. On the other hand, if you have a logic, if you are applying it to a wide field of vision, then yeah, you will be totally fine. Early adopters obviously gain leverage, not jobs overnight. The biggest value is conceptual, not operational yet. So this is the conclusion. Quantum computing is inevitable but not imminent. Software engineering at this point is safe, but it's evolving into a plethora of different ideas. Winners prepare early without panic, and this is a sort of a long game, and curiosity compounds faster than hype. Okay, so this is for the this is all for my ninth episode. Yeah, thank you, and I wish I meet you sooner. Okay, thank you.